Hello and welcome to this video where we're going to learn about circle theorems. Before we do our first theorem, we're going to need to know the names of some key points of a circle. So if we draw a circle, and then draw a straight line that goes from one side of the circle to the other, this line is known as a chord. A chord will always split a circle into two segments. Here we have a segment at the top, and also a segment here at the bottom. Now let's have a look at our first circle theorem. The first theorem states the angles in the same segment are equal. This means if we use this chord that we've drawn to create an angle, but keep that angle within the same segment, all of those angles will be the same size. So let's draw an angle in the upper segment using this chord, like this. If we draw a second angle like this one, or even a third like this one, then all of these angles must be the same size because they come from this chord and they're in the same segment. So if the purple one was 68 degrees, the green one would be as well, and so would the blue one. Sometimes this theorem is drawn without the red chord, so we can remove that and it may look something like this, and the property still holds. It's often drawn with only just two of the angles, so if we remove one of them like this, we end up with this picture where both of the purple angles here are the same size. You can also apply this theorem by drawing a chord here. If you do the same thing as we just did but upside down, you can show that these two angles are also the same. And again, we don't need to draw that chord, so very often you'll see this theorem drawn like this. It's sometimes informally referred to as the bow tie theorem because this looks a little bit like the shape of a bow tie. In an exam though, you want to avoid that terminology and say that the angles in the same segment are equal. But if the bow tie helps you recognize when this is true, then that's fine also. For the next theorem, we're going to need to mark on the center of the circle. We're going to draw a chord that goes straight through the center. This is known as a diameter. If we now do the same thing as we did for the first theorem, so draw angles that are in the same segment, we know they're going to be equal. So if we draw one angle like this, a second like this, and even a third like this, we know all three of these angles must be the same size. But it turns out that if the chord that you draw happens to be the diameter of the circle going through the center, all of these angles will always be right angles. So the second theorem is that the angle in a semicircle is 90 degrees. We say this is the angles in a semicircle because that diameter splits the circle in half. For the next theorem, we're going to draw a chord once again, and draw an angle at the circumference also. But rather than drawing another angle at the circumference, we're now going to draw an angle at the center, but using the same chord, so something that looks like this. If the green angle at the circumference of the circle was 50 degrees, then the blue one would be twice this, 100 degrees. So for this theorem, we say the angle at the center is twice the angle at the circumference. You could also say it in reverse, the angle at the circumference is half of the angle at the center. Once again, this theorem still applies if we remove the chord, so sometimes you see it drawn like this. For the next theorem, we need to learn some more terminology. If you draw a quadrilateral where all four of the sides touch the circumference of the circle, this is known as a cyclic quadrilateral. Now it's only true if all four of the corners of the shape are on the circumference. For example, this shape here is not a cyclic quadrilateral because this corner here isn't on the circumference of the circle. So let's return to our original one. This is a cyclic quadrilateral. The theorem states that the opposite angles in a cyclic quadrilateral add to make 180 degrees. For example, if we look at these two angles here, they're opposite each other and they're in a cyclic quadrilateral. So if we knew that this one was 86 degrees, we'd know the other one must be 94 degrees, since 86 plus 94 makes 180. Similarly, these two angles must add up to 180 as well. If we knew this one at the top was 110, the bottom one must be 70, since 110 plus 70 is 180. For the next theorem, we're going to draw a tangent to the circle. A tangent is a straight line that touches the circle in one place. We're then going to draw a radius from the center of the circle to the point where the tangent also touches the circle. In this diagram, this angle here will always be a right angle. So we can say for this theorem, a tangent meets a radius at 90 degrees. Now if we stick with this same diagram, we can do some more theorems. If we create a point at the end of this tangent on the right hand side and call that P, and then if we draw a second tangent from P to the circle, it would look something like this. If you measured this distance here, from P to the point where the tangent touches the circle at the top, and the same distance at the bottom, these two lines would be the same length. We don't normally show this with arrows though, we usually draw a line across both of those lines to show they're the same length, like this. If you were going to write this theorem down, you could say that tangents from the same point are equal in length. We can also add a bit more information to this diagram. If you draw the angle at P, then draw a line from the centre of the circle to P, then this line will split that angle in half, or we could say it bisects the angle. So if the whole angle here was 30 degrees, then we'd have 15 degrees on the top, and also 15 degrees on the bottom. Now we're going to move on to the final theorem. If we draw a tangent to the circle, and then draw a chord from the point where the tangent touches the circle, we form an angle here like this. Next we're going to use the chord to create an angle at the circumference, but not in the same segment, in the other segment, so something that looks like this. It turns out that the angle that the tangent makes with the chord is equal to this angle that the chord makes at the circumference. The same happens with the chord on the other side as well. So if you look at the chord on the right hand side, the angle it makes with the tangent is this green one here, but this chord will create an angle at the circumference in the other segment over here. So these two angles are also equal. We call this the alternate segment theorem, and you'll need to know this name. Here's a quick sketch of all of those theorems we've covered on one page. You may find this useful for your revision. Now we're going to have a look at how we can use these theorems to solve some problems. In this question we've been asked to find the angle ABD, but we've also been asked to give reasons for our answers. So every time we find an angle we need to explain what we did. This will often involve just writing down the theorem that we've used. So in this one we're looking for the angle ABD. We're first of all going to find the angle ACD. You should notice that this angle here ACD goes with the angle ACE to make a straight line. So these two angles must add to make 180. So we could say that 180 minus 105 equals 75, so we know that this red angle here is 75 degrees. And remember we need to give reasons for our answer, so we would state that the angles on a straight line add up to 180 degrees. Now we can use one of our circle theorems to find the angle ABD. This one looks like the bow tie theorem, the first one we did. So the red angle we just found is actually the same as the angle ABD. So this one is also 75 degrees. So we could say that angle ABD equals 75 degrees, and once again we need to give a reason because the question asked us for one, and we would give the first theorem, which was that angles in the same segment are equal. In this next question we've been asked to find angle BCF, but this time we don't need to give reasons because it hasn't asked for them. We do need to show working out still though. We're going to start by looking at the triangle ACD, which is this one here. We know this is an isosceles triangle because we can see that AD and DC are the same length. This means that the angle ACD down here is 35 degrees. It's a good idea to mark any angles that you find directly onto the diagram, but we're also going to write down that angle ACD equals 35 degrees. Now we're going to stay inside this triangle and work out the angle ADC, which is this one here. We know angles in a triangle add to make 180 degrees, so if we add up the two angles we have, 35 add 35, that gives you 70, and then if we subtract this from 180, we get 110. So we can add this to our diagram as well, and we're going to write down that angle ADC equals 110 degrees. Next we're going to look at the whole quadrilateral here. You might remember from before that one of the theorems was about cyclic quadrilaterals. We can be sure this is a cyclic quadrilateral because A, B, C and D are all on the circumference. The theorem was that the opposite angles in a cyclic quadrilateral make 180 degrees. So if we look at the angle that's opposite the 110, that's this one here, ABC, we can work this one out by subtracting 110 from 180. So if we do 180 take away 110, you get 70 degrees. So we can mark this onto the diagram, and also write down that angle ABC is 70 degrees. Next notice how the line AB goes through the centre of the circle. This means it's the diameter. The second theorem we looked at was that the angle in a semicircle is always 90 degrees. This means that the angle BCA, which is here, is a right angle. So we can write down that BCA equals 90 degrees. Now if we stay inside this triangle ABC, there's only one more angle to find, the one at the top here. You can find this by subtracting the other two from 180. So if we do 90 plus 70, that's 160, and then 180 take away 160 is 20 degrees. So the angle at the top here is 20 degrees, and we can write down that angle CAB is 20 degrees. And there's only one more step to go to complete the question. We're looking for the angle BCF. We can use the alternate segment theorem to show that this is the same as the angle we just found. This 20 degrees here is the same as 20 degrees here. So the angle BCF equals 20 degrees. Now we didn't write down any of the worded reasons for this question because it didn't ask us to give reasons for our answers. However, you can see we have put down quite a substantial amount of working out, and we've also labelled every angle that we found onto the diagram. It's worth noting that this isn't the only way to solve this question. In many circle theorems questions there are different approaches. As long as you get the right answer and show your method clearly, you will get full marks. To begin this question, we're going to look at the line ECF, which is a tangent to the circle, and also the line OC, which is a radius. One of the theorems said that a tangent meets a radius at 90 degrees. So we know this angle here is 90 degrees. So let's write that down, angle OCF equals 90 degrees. Now we're going to look at the whole triangle OCF, this one here. We have two of the angles in this triangle, we have the 32 degrees and the 90 degrees, so we can find the missing one. If we add together 90 and 32, you get 122, and if you subtract this from 180, you find the missing angle is 58 degrees. So we can write that angle COF equals 58 degrees, and label this onto the diagram. Next we're going to look at the angle CAB, which is this one here. You should remember that the angle at the centre is twice the angle at the circumference. We can see the angle at the centre from the chord CB is 58 degrees. So the angle the chord CB makes at the circumference, which is the angle I've marked, must be half of 58. So if we do 58 divided by 2, which is 29, we know that this angle must be 29 degrees. Next we're going to look at the smaller triangle COB, this one here. Sometimes in questions there's information that's not necessarily marked onto the diagram, but it is useful. It's useful, for example, to notice that OC and OB are both the radius of the circle. This means they're the same length. We can mark that onto the diagram, but it's very often not given to you. You need to be able to spot this information yourself. This means the triangle COB is an isosceles triangle, so two of the angles must be the same. So if we subtract 58 from 180, we get 122, and then if you half 122, you get 61. This means both of the base angles in that isosceles triangle must be 61 degrees. The one that's important to us is the angle OBC. So angle OBC is 61 degrees, we can add this to the diagram as well. Now finally, if we look at the triangle ABC, we're only one step away from finding the angle ABO, which was required in the question. So the angle ABO is this one here. All of these four angles must make 180 since they're the interior angles of a triangle. So if we add up the angles we have, 40 plus 61 plus 29 makes 130, and if we subtract this from 180, you get 50, which is the answer to the question and angle ABO. Thank you for watching this video, I hope you found it useful. Check out the one I think you should watch next and subscribe so you don't miss out on future videos. Also check out the exam questions I put in this video's description.